Now we're going to look at a physical pendulum. This is the situation where the distance from the center of mass to the axis of rotation is relatively similar size to maybe the size of my object. Okay? So maybe my my object is completely outside of the center of mass, or maybe I actually have something where, that pivot point is on my object. And so we're going to look at how do we set up this type of problem. Okay? So what we need to do first is we need to set up a torque problem. So again, we're going to derive how do I find the period for a physical pendulum. So I'm going to go ahead and start my torque problem. So I'm going to sum up the torques and set it equal to I alpha. Now again, just like we did for the simple pendulum, we are going to look at the angle it's displaced. And so in this case, I'm going to call that direction my positive direction, which means my torque is going to be the opposite. So I'm going to have a negative torque. Now you'll remember that gravity acts at the center of mass. So the torque produced is going to be from this point to this point. Now I'm going to call this distance d. Okay? And that distance d comes from when we do the parallel axis theorem. So you will need to use the parallel axis theorem to find the moment of inertia of your object about that center of rotation. All right. So the torque produced is going to be mg sine of theta in the negative direction times that d value. Okay? And the reason for that, again, is we do need to find the perpendicular one, which is this one, mg sine theta. So the perpendicular component times the distance from the axis of rotation to where that force is being applied. So that is my mg sine theta. And that's all going to equal I times alpha. Now remember, this I value, you will need to use the parallel axis theorem most likely to find. Unless it is a uniform rod, by all means, then you can do your integral method to find that, if so need be. All right, so let's go ahead and make our next step. Again, we are trying to get to that point where we have the form of alpha is equal to negative omega squared, where omega is that angular frequency, remember, times theta. So that's my goal. I want to get to this format here. So what we're going to do is we're going to get alpha by itself. So I have alpha is equal to, and I'm going to put everything else on the other side. So I have negative mgd divided by I times the sine of theta. And just like we saw in the regular simple pendulum, we're going to make that small angle approximation. So instead of sine of theta, we're going to say that the sine of theta is approximately equal to theta. What this does for us is it does limit our range down to something with an amplitude of, say, 20 degrees or less. Okay? In doing so, I now have alpha is equal to negative mgd divided by I times theta. So now I do have it in that format. And so I do know what my angular frequency is because I have that format. So that means that my angular frequency is going to be the square root of mgd over I. And again, remember, d is going to be the distance from the axis of rotation to the center of mass. And that I value you will most likely have to find using the parallel axis theorem. My next and final step to get to period is I do need to go with the identity that period is 2 pi divided by angular frequency. This comes from the idea that period is 1 over frequency, and that angular frequency is just 2 pi times that regular frequency. So here we go. Let's put that in there. And so I'm left with the period for a physical pendulum is 2 pi times the square root of I, the moment of inertia, about the axis of rotation here. Not about the center of it or some other point, but about the axis of rotation location, divided by mgd, where d again is the distance from the axis of rotation to the center of mass. And so here is my physical pendulum equation. Again, this kind of gets rid of that constraint that it has to be a simple pendulum or a point mass. So this one works for all objects that are rigid and in some sort of pendulum-like oscillation, but it does still have that restriction on our small angle, so we do have to limit our angle as well.